Limiting and excess. So hopefully the simulation give you a good kind of idea of this as we go along. The two pieces of bread and the cheese as the reactant, giving you the sandwich as the product. Definitely will be helpful, as well as looking at the ammonia example and the methane example of those reactions. So what you should be able to do by the time we're done with this particular lesson, be able to identify limiting and theoretical yields from the stoichiometric calculations, and also be able to identify the excess, but be able to calculate how much of the excess is left over or remains in the reaction vessel or the beaker or the flask, whatever we would be using there. All right, so very similar to what you were just doing. This is a nice analogy example where you have the bread and the cheese making the sandwiches. Here we have 8 car bodies, and we also have 48 tires. Well, I'm sure, as you can imagine, if we're just going for the 4 tires per car here, which one are we going to have extra of? The tires, right? We only have 8 car bodies, so 4 times 8, that'd be 32. That means we're going to have extra tires. Those would be in excess. The car bodies, of course, would be the limiting here. So yeah, as you can see, we have the 8 cars, but we have 16 extra tires. So if we're talking in terms of the limiting versus excess here, the car bodies is limiting, and the tires are in excess, as you can see. So this is sort of like the sandwich analogy example, and then we apply it to actual chemicals, okay? Reactant in a chemical reaction that limits the amount of product that can be formed. That's basically what a limiting reactant does, hence the name limiting. Okay, the reaction stops when it runs out. If you use it all up, it's gone, it's been consumed. There isn't anything else to react. It's like the missing ingredient now. Also here, determines the theoretical yield. And what is special, or what is a little bit different about these problems than just regular stoic or regular percent yield type problems is you can identify a limiting reactant problem because they give you amounts for both reactants. And if they give you amounts for both reactants, you realize you have to calculate for both and then figure out which one comes out smaller. Let's talk about the excess reactant. And sometimes it's called the excess reagent. You might see it phrased like that. It's the same thing. A reagent is just a reactant. It's the one that remains after the reaction, after the limiting has been completely consumed. So this is extra that's still floating around in the beaker or the reaction vessel. We would say it's added. A lot of times they add extra of one reactant to make sure the reaction completely runs. So we want to make sure that the limiting gets used up. So you might add extra of one. And if you're, in industry, the cheaper reactant is probably the one you would want to use in excess rather than the more expensive one, obviously. The excess reactant remains because there's nothing with which it can react. So it's left over in there floating around in the beaker or the flask or the reaction vessel. All right, so looking here, this is a particular model one, kind of like the other ones that you were doing in this one was like the ones that you were doing in the PhET simulation. Whereas you can see here, we have our 2 reactants. We have hydrogen plus oxygen, and the overall reaction up top giving you water. Now the mole ratio is 2 to 1 to 2, 2 hydrogens to 1 oxygen. Gives you the 2 waters. So if I'm starting over here in my box, and remember hydrogen's diatomic, that's why you see the 2 blue circles there, because they're twins. So if I were to just look at this and try to figure out my counts, basically since there's 4 of them in that little box, we would say that's 4 moles of hydrogen. And since in the middle box there, the oxygen, there's 3 moles of oxygen, like so. But you have to really pay attention to the mole ratio because, yeah, like you've got 4 moles of hydrogen, 3 moles of oxygen, and you might be like, well, the hydrogen's more abundant because there's more of it. But when you work it out to looking at how many hydrogens do you need for each water, you need double the hydrogen because you have the 2 H's and the 1 O for each hydrogen. So what you see there is all 8 of the hydrogen get used, and that only 1 oxygen is needed for each of the water. That means 1 of the oxygen is in excess or left over. So 4 moles of the water get produced from that combination, but you do have a little bit extra, and the one that you have extra of is your oxygen there. Therefore, we can identify the hydrogen as limiting, the oxygen as excess in our reaction. Alrighty. Calculating wise, we're going to calculate the amount of product formed for each reactant. That means we have to do 2 chi charts each time. That's why I don't particularly love these problems, because they're longer than normal. Alright, you calculate them both to the same product, and then you look for which one is the smaller amount. The smaller amount indicates the limiting reactant, but it also indicates which one is the theoretical yield, the maximum amount that can be produced by that reaction. So you get 2 pieces of information when you calculate them both. The one that's smaller tells you the limiting reactant. It also tells you the theoretical yield. Now there's 2 methods of how to do these. So I'm going to show you both. I like one over the other, and you might not like the one that I like, but I'm going to show you various methods of how to do this. So, and you can choose which way your brain thinks about it and way you like to process it. All right. We're going to start with the easy one, like this one, where it's just mole to mole. And then we're going to get into the more difficult ones where we're going to work to grams on things. So, consider the reaction 2 carbon monoxide, 1 oxygen. It's going to give you 2 carbon dioxides. How many moles of carbon dioxide will be produced if 12 moles of carbon monoxide and 7 moles of oxygen reacted? Determine the limiting reactant and excess reactant. All right, so basically we have 12 moles here, 7 moles here. And we want to know how much we can get of our carbon dioxide. So once again, one of the main differences in these types of problems than in other ones is they give you amounts for both reactants. So that means you have to calculate both. So we'll start over here with our carbon monoxide, 12 moles CO. And it says how many moles of carbon dioxide, so we know we just have to go to moles over here. It's only going to take 1 step because we're starting with moles, going to moles. That means we only need the mole ratio. Put this down here, CO, go to moles of CO2. Look at your balanced reaction. We have 2 moles of CO, 2 moles of CO2. Well, 2 over 2 really is like 1 over 1, so this is actually 12 moles of CO2 from this one. Now let's look at the next one. The 7 moles. I'll do that down here. 7 moles O2. Still working to that same product. So I take my moles of O2, put it down here, 2 moles of CO2 on top. still just moles to moles here. This time we have the 2 moles of the carbon dioxide, but we only have the 1 mole of the oxygen. So this ends up being 14 moles of CO2. So looking here, we have that answer, and we have the one from the carbon monoxide. Out of those 2 numbers, which one's the smaller one?
12.
The 12 is the smaller one. This is the smaller one. So this is your theoretical yield. Okay? That is the maximum amount that could be produced with this combination. That also tells you what about your carbon monoxide? Which reactant is it? The one that produced the smaller amount. Yes, that's going to be your limiting. This is your limiting reactant. So that means the oxygen is the excess reactant, because you're going to have extra of it. So the one that produces the smaller amount tells you the theoretical yield as the product, but it also tells you that reactant that started the chart is the limiting reactant. And this one's not too bad because all we had to do was work mole to mole. But most of these problems are grams to grams, so they're going to take 3 steps. Or you might like option 1, which is what I prefer, but you guys can decide which method you like better. So, let's see here. Recap, just showing how to look at your chart here. Going to moles of carbon dioxide. There you go. We get 12. Do the other reactant. And we get 14. So the 12 happens to be the smaller amount. And then we can identify our reactants. The one with the smaller gives you the limiting. Okay, so option 1. So you have to put option 1, and then I'll work it showing you option 2 as well. Work to moles first, and then you only convert the second one, or you convert the one that's smaller. That's kind of what we're going to do here. And I like this method, especially because in AP, a lot of times they ask for moles of stuff, but they also want grams of stuff. So if you already have worked it to moles, you can use those later on in other parts of the problem. So I particularly like to use this first because you have more information to work with. But like I said, some people are going to like option 2 better, and you're welcome to use option 2. Let's look at our problem though and see what we have here. According to the chemical equation, how many grams of aluminum chloride will be produced from combining 100 grams of aluminum, 100 grams of the chlorine? Determine the limiting reactant. So it does want grams of the final product there. We are going to eventually have to get to grams, but I'm going to work them both to moles first. So this is one option. We're starting with 100 grams here, 100 grams here, but I'm going to work them both just to moles first of our aluminum chloride. So grams to mole is something to mole. That's going to take 2 steps. So you have to set them both up. Okay, so I'm going to make this one the red one. So 100 grams of aluminum. From the 100 grams of aluminum, we have to go to moles of aluminum. Then we can go to moles of aluminum chloride. So that would be the first T chart to set up, like so. That means the grams of aluminum go down here because you have to diagonal that down. And then the moles of the aluminum go down here, like so. All right, so periodic table, what is the molar mass of aluminum? We gotta look that one up. 26.98. 26.98 equals 1 mole. Then we look at our balanced reaction, and we have 2 moles of the aluminum chloride to 2 moles of the aluminum. So that's our first one. We have to work the first reactant. And basically this is just going to be 100 divided by 26.98 because the 2's are going to cancel. I'm going to go with 3 significant figures over here. So 3.17 moles AlCl3. Is that what we got? All right, so now we got to do the other reactant. Fun. Here, we'll do this one in green. 100 grams chlorine. That's going to go 2 moles of chlorine, which is going to go to the moles of the AlCl3. So we take this, diagonal it down, we get grams of chlorine down here, and then moles of chlorine go down here, and there we have it. Now we got to insert our numbers. So 1 mole of chlorine. Chlorine is 35.45 on the periodic table. So times 2, since there's 2 of them in our molecule here. So that's going to be 70.90. Then we look up here at our balanced reaction. We have 3 moles of our chlorine up there. So we're going to put a 3 here, the 3 up there, and then back to the 2 for the aluminum chloride. So what do we get for our moles from the chlorine reactant? So 100 times 2 divided by the 70.9 divided by the 3, and you all get what fun value there. Anyone? Anybody at home get that number? .940, yes, because we're going to keep 3 sig figs, so we're going to add on that 0 to be significant. Yep, and this is what I got here, moles AlCl3. All right, so which one is our limiting reactant based off of these numbers? Which one's the limiting? Chlorine, yes. As you can see, this number is very small. Right here, this number, smaller number. So this chlorine right here, that's going to be your limiting reactant. That means aluminum is the excess. Okay. Now, the last step here, this is the working to moles first. However, it does want grams of aluminum chloride. So I take the smaller one and I change it to grams. That's what I do. Just change this one over to grams. So moles of aluminum chloride to grams of aluminum chloride. I do that final step on that one. Now I have to do the molar mass of aluminum chloride though. Aluminum, 26.98. Chlorine, there's 3 of them, and it's 35.45. So let's add that up. Get our molar mass. This would be the molar mass for that. molar mass. Okay, that's kind of a fun number. 133.33 grams equals 1 mole. So we do 133.33 times the 0.94, and we get our final answer for the theoretical yield of 125 grams AlCl3. Now the significant figures, of course, are based off of the measured values in the problem, which happen to both be 100 with the dot, and the decimal point there makes those 2 zeros significant. So the final answer is the 125 aluminum chloride. Now you can work your limiting reactant problems via this option, where you work it to moles and then you just change the smaller one over to grams. Some other people like to do option 2. But here it just recaps what we just did. There we go, you can see it. We get our answers. Do both of the reactants to the same product, and we end up getting the same thing, the limiting reactant, change that one over 2 grams, and get our theoretical yield. Wonderful. So if you want to recap, there's that version. Option 2 is to not stop at the mole. Option 2 is just to work both of them directly to grams. So, going to show you, instead of stopping at the mole there, you would go all the way over to the grams of the aluminum chloride, like so. Just add on that last part of the t-chart, the 1 to the 133.3 grams. And what you'll notice is everything still cancels the same. And in that case, the total grams would have been 494 for the aluminum. Now, of course, you would set up the second one to the chlorine, like so, and go directly over to grams, like so. It's basically everything that we just did, but we tack on the gram part at the end as well. Cancels everything out, and you'll see it's still 125. And that's going to be your theoretical yield, along with your limiting reactant. So you can do it this way, where you work them both directly to grams. Like I said, I have my own reasons for liking option 1 better, but some people really like this, where they just go straight through, do it all one big long chain. As you can see, though, the answer is not different. Still 125 grams of the aluminum chloride, and you're still getting the limiting reactant to being the chlorine. So feel free to work with option 2 if that feels more comfortable for you. Any questions? Either way which you decide to do your work, will be accepted if it's set up correctly. Theoretical yield, all that good stuff. All right, now, how much of the excess reactant will remain? There are 2 ways to work the excess problems too. And like I said, it's going to depend on you which way you see it better, which way your brain processes it better. of how you want to work it. So this method says start with the limiting reactant and you work it to the excess. So you're going to set up your T-chart starting with the limiting. Okay? So our limiting reactant was the chlorine, right? So that's what we're going to start our T-chart with. 100 grams of the chlorine, right? 100 grams of the chlorine. We're going to work it to our excess, to the aluminum. So we're starting here with our 100, and we're going to work it now to the aluminum. So before I can switch to aluminum, I've got to do moles of chlorine. Then I go from the moles of the chlorine to the moles of the aluminum. Then I'm going to go to the grams of the aluminum. Set up my T-chart. Like so, grams of the chlorine go down here, moles of the chlorine go down here, and moles of the aluminum go here. All right. Now all we have to do is insert our numbers, and luckily we already have all those figured out because we know the molar mass of chlorine because we did it in the previous problem. So we don't have to look that one up again. This one was 70.90. That equals 1 mole. Now the balanced reaction, 2 moles of aluminum to 3 moles of the chlorine. And then we already know the molar mass of aluminum because we already looked it up again. So 1 mole is 26.98. We work the limiting to the excess. Go ahead and do that. I'm going to tell you what this number means once we get it calculated. So 100 times 2 times 26.98 divided by the 70.9 divided by the 3. And since we have 3 digits over here to start with, I'm going to keep 3 in my ending over here. So this is going to be 25.4. Gotta get 25.4. Okay. Grams of aluminum. Now, what does that number mean to me? That number is the amount of the aluminum that was actually consumed in the reaction. So this is the amount that was used in the reaction. And we abbreviate reaction RXN. So out of the 100 grams, 25.4 was the amount that was used. Now when we want to figure out how much is left over, all you have to do is take the starting amount, starting grams, subtract the used grams, and that's what you're going to get the grams remaining, or the leftovers. So 100 minus the 25.4, how much is left over? You said 30 or 74.6?
Yeah.
All right, so if we're getting technical on significant figures, though, what do we need to round to? Because this is subtraction. Addition and subtraction, remember, is about place value. So we would have to technically round it to this here. I think the answer says 74.6 in the PowerPoint, but technically we would say 75 grams because of the way that number is. But we could do that too and pretend it has the tenths and leave it here as this. But 75 grams or 74.6 would be left over, still in the reaction vessel. Obviously this person didn't estimate very well, so they've wasted a bunch of aluminum. Or maybe they can filter it back out and reuse it. But that's one way of how to work an excess problem, is you start with limiting, work to excess. I'm not sure if I don't think we're gonna have enough time to do the second option completely. So I think that would be a good point to start from for next class. We'll start there next class.